Okay, so this is section 9.2. We're talking about the hyperbola now. So hyperbola is another of the conic sections. It has a formal definition, but again, it's a conic section, and it's called a conic section for a reason. A cone for us, right? We talked about this. A cone for us is two really cones put together. And conic sections are the curves that you get by slicing that cone in different directions. If you slice that cone in a direction that's particularly that's vertical, right? So if you take that cone, so let's say slice that using a vertical plane like that, right? So imagine you do that last side differently so that you can clearly see what I mean. So you have something that goes on behind, right? So you're slicing that cone. The trace that you're drawing here that's our hyperbola. So, and you have like another one here, right? So that's what the hyperbola is. It's a slice that you get by cutting a cone vertically. So it's got two pieces, as you can see, like one here and one here. It looks like a parabola, but it really isn't. You're going to see by the equation. There's no really other way to see it other than the equation. So let's get to it. Objectives here for today are for you to be able to locate the vertices and the foci of a hyperbola, how to write equations for a hyperbola, how to graph them when they're centered at the origin. When they're not centered, I'm not going to go over that too much. I'll just sort of brush over it. The idea is the same as with circles and hyperbola and parabolas when they're not centered at the origin, and circles and everything, which is something we've done before. But I'll mention it. And how to solve applied problems. And that here requires one more thing, so I guess I'll just write one more thing on the list. I'll say I also want you to recognize hyperbolas from a verbal description, which is really the breakthrough here for us. The way I defined hyperbolas for you, right? I just defined it, right? I just said it's the slice from a cone. That's not really how most people define them. When I say this, I'm just saying this is why they're called conic sections. But the definition of hyperbola comes in terms of distances, so they're going to tell you it's important they pay attention to this. It's the set of points in a plane. The difference of whose let me read that again. Difference of whose distances from two fixed points called foci is constant. Okay, so the difference of whose distances from two fixed points is constant. So let's say this. Let me unpack that for you in this picture. So the two points that we're talking about are the foci. So this is focus number 1, focus number 2. So I'll call it focus 1, focus number 2. So what I'm trying to say is that for any point, right, that you choose, the distance to focus number 1, let's call this D1, and the distance to focus number 2, let's call it D2, right? So D2 minus D1, that's some number, okay? I'll call it K or something. So if I choose another point, green, say, here, the distance to focus number 1, let's call it, I don't know, let's call it C1, I guess. And the distance to focus number 2, C2. So C2 minus C1 also equals K. So what this verbal description here is saying is that for any point that I choose on that blue graph, right, on that blue that blue shape, I guess, because this is not a graph, right, it doesn't pass the vertical line test, but any point that I choose here has that property. If you measure the distance from each of the two foci and you take the difference, that's going to be constant. where you may have to take like absolute values in case you want to go one minus the other, right? Okay, that's the idea. So the difference between the distances is constant. Seems a little odd. You're gonna see how it's useful in a second. Here are the main characteristics of a hyperbola. You have first the vertices, which are the same, called the same as they are for parabolas, right? So the points that are closest to the center of the hyperbola. You have what's called the transverse axis. It's called that because it traverses the hyperbola right in the middle. Right? It's also an axis of symmetry of the hyperbola. So the left side or the upper part in this drawing equals to the lower part. There's symmetry involved. There's the center, right? And there's the foci. There are the foci. So we talked about this before. Focus is a word that the plural is foci, right? So I'll just get used to that. So the foci are the most important, really, points here. But the other points, the other characteristics, the axis, the center, the vertex are also important. The foci are just the most important ones. Okay, so let's see here how the equation behaves. It's not so easy to come out, it's not so hard either to come out with this equation. All you need is to write the definition of the things that I said before. So all you need to write is that if you want to come up with this equation on your own, you gotta say distance from x, y, and the origin. So not the origin really, right? So you're taking this guy c here and this minus c. So these are the foci. So distance from x, y to minus c comma 0 minus the distance from x, y to c comma 0, and that's some constant. And you start playing that, use that formula for distance, right, which is the square root of x squared minus c squared. You start playing with that, you cancel things out. In the end, you get something like this, okay? And that's gonna depend, right? Just note the difference here. How the equation comes to be is not as important as how it affects. I mean, it is important if you want to know. I recommend you do it. But it's also important to see how it alters the shape of the parabola. Note that when x is positive, right, then a is below x. When y is positive, then a is below y. Okay? Okay, so when x is positive, which is this case, then the transverse axis is the x-axis. When y is positive, then the transverse axis is the y-axis. Okay? And then you have b, which is also just the second thing, right? It's just whatever's under the negative one, the negative variable, right? Because I have this negative sign here, which determines everything for you. And then the next thing that you have is c. So this guy here is c, right? How do you find c out, right? Similar process than with ellipses, just slightly different. So you have that b squared equals c squared minus a squared. So really what you want to be having at hand is this. C squared is a squared plus b squared. Okay. So this is what I have to know for graphing hyperbolas. So let's put that to practice a little bit. Here's an example. Find the vertices, locate the foci for the hyperbola with the given equation. So this is the equation. Because x is positive, then a squared is the one underneath x. So a squared equals to 5. So that means a squared to 25. Sorry, this right. So a equals to 5. So the square root of 25. B squared is the other one, is 16. So that means b equal to 4. Right? So c squared equal to a squared plus b squared. So that will be c squared equal to 25 plus 16. Note that I didn't need any of this, right? I only needed a squared and b squared. So note that, just because of the question they were asking. So they just want the vertices and the foci. But I'll get to that. So c squared equal to, what's that, 3141. So c equals the square root of 41. Okay, so that means, okay, so now let's locate them. So I found c, I found a, I found b. I'm not graphing it, right? I'm saying, let's go back to my original point. So x is positive, so that means I am in this situation right here, and this situation right here. So that means the transverse axis is horizontal. So when I want to find the vertices, I go left and right, and A determines that for me, right? So the vertices are, so -5, because that's what A is, comma 0, and then 5, comma 0, and then the foci are determined by C, so they are root 41, negative root 41, comma 0, and then positive root 41, comma 0. So you can tell here the square root of 41 is greater than 5, right? Because the square root of 25 is 5. So this guy's further away from the origin than 5 is, as expected, right? So you can see the answers there. So double check. And now here's another example. I'm not going to do this one. The answer is here for you to follow along. Just note that now A is underneath Y, right? So when you go and draw the same thing, now the coordinates go into the y-axis, because now the transverse axis is the y-axis. So what I'm trying to say is that this hyperbola looks like this, whereas that hyperbola looks like this. So that's the difference between the two examples. The computations, the numerical computations, right? Calculations are the same. Okay? So there you have it. You can see the drawing there. Okay. How about doing the opposite? How about finding the hyperbola's equation from the foci and the vertices? So this is what they do. This is what they give us here, right? So this is the foci. These are the foci, and these are the vertices. So the fact that these are the foci, right? Remember that C is what governs the foci, the distance between the foci and the center. So that means C equals to 5 from this foci, from these foci there. And this, the vertices are governed by A. So A equal to 3, right? So then I can go A squared plus B squared equals C squared. So that's 3 squared plus B squared equal 25, right? So 5 squared. So 9 plus B squared equal 25. Subtract B squared equal to 16. Subtracting the 9. So B equal to 4. Okay? So the fact that my foci are on the y-axis, right? So this is positive 5, this is negative 5. This means this is my transverse axis right here. So my hyperbola, excuse me, looks like this. Mm-hmm. So that means A has got to be under. So A squared divides Y squared, because the vertical axis is the transverse axis. So that means Y squared divided by, so there's A, right? 3 squared, so 9, minus X squared divided by B squared, which is 4. 16 equal to 1. So that's the equation of the hyperbola. Okay? So that's the most important thing. A divides the positive one, right? The positive term, and which one is positive is determined by which one is the transverse axis, or the vertical or horizontal. Okay? So that's what you have there. I don't need this page. Don't need that. Just did it. Wait, let me see if it's the same thing. It is the same thing, right? Just got a double there, so let's erase that. Another equation here, the asymptotes of a hyperbola. So this is one of the characteristics of a hyperbola that differentiates it from a parabola. So it has asymptotes, slant asymptotes. and these are the two of them, that's going to depend on what's under y, right? So note that whatever is under y goes on top of your equation. Right? If a is under y, then it goes on top of the equation here. If a is under x, then it goes at the bottom. So just gotta remember that, and that helps you out here. Okay. So it's basically whatever is under y over whatever is under x. Okay. Depends on whether the hyperbola is horizontal or vertical on its transverse axis. So vertical transverse axis versus horizontal transverse axis is what determines which one is which. I just think of it that way. It's whatever is under y over whatever is under x, square root of whatever it is, right? So a and b rather than a squared and b squared. So let's see an example there. These are the asymptotes, really. Like I said before, a parabola doesn't have asymptotes, whereas a hyperbola does. So this is one of the differences. So this is y equals b over a, right here. And this is y equals minus b over a right there. And this here, y equals a over b and minus a over b. Okay, just keep that in mind. This is important here. I may ask you to do this. So how do I graph hyperbolas? I put all these characteristics together. I find the vertices. I start highlighting. So I find the vertices. I use dash line to draw the rectangle centered at plus and minus a plus and minus b, because that helps me find the asymptotes. Okay, this is what determines the asymptotes for me. Then I draw true branches, the true branches, by starting at each vertex and then approaching the asymptotes, right? So draw the true branches, and I'm basically done. Okay, so these are the four main characteristics that I want to see. You really want to draw like a little rectangle in the middle. This one that you see here, right? This one that you see right here. You really want to draw that, because that really helps you, get a feel of the asymptotes and of the branches. So let's get graphing this one as an example. So let's first graph this by locating the vertices. Okay, so looking at this, I see that x is positive, right? So x squared is positive. So the transverse axis is horizontal, so the hyperbola is horizontal, if you want to say it like that. So I know it's going to be like this, right? It's just for my own reference in the future. I know a is whatever is underneath the positive one. So a squared, right? So a equals 6, and b squared is the other one. So 9, so b equals 3. Okay, so got quite some progress here. They want the vertices first. So the vertices are here, and they're governed by a. So they are minus 6, 0, and 6, 0 are the vertices. Okay? Now, let's draw my rectangle, because now I know a and b. So I'm really supposed to be doing this on the same graph, but I'll be doing like parts of them all here. So I'll draw them here on this side. So you're really going 1, 2, 3, 4, 5, 6. 1, 2, 3, 2, 3, 1, 2, 3, 4, 5, 6. Proportion isn't that important if you can keep proportion. Then that's better. If you can't, it's not the end of the world, as always. So that's the points that they're referring to right here. So minus 6, 0, 6, 0. So there's minus 6, 0, and 6, 0, and then 0, 3, 3, 0. The 3, remember, I got from b, right? B equals 3. So that's where I got the 3 from. A equals 6. That's where I get these numbers from. 6 and 3. Okay, so I got this this rectangle. So now what I'll do is I'll trace a line that goes like this. So that's one of the asymptotes, and this is the other asymptote, okay? And then the next thing that I'll do is I'll get the vertices, which is one here, right? I'll do this. Maybe the other vertex, or the other vertex, excuse me. And then extend this. So this is not looking great because I'm cramming everything in the same piece of paper, but I'm just outlining what's going on. I'll put everything together below again. So let me do this whole thing again underneath. So here's 6, here's minus 6, some proportion is good. Use dashed lines to draw the rectangle. You can draw the asymptotes with the same color if you want. They can also be dashed if you'd like. Just try and make sure that the lines, the asymptotes, go through the points they're supposed to go through, right? Helps you drawing the asymptotes dashed as well, because then you don't have to worry too much about them being straight lines. You can sort of fix them as you go. And then, like I said, you take one of the vertices, which is always at A, extend as they approach the asymptotes. This is good. This is a good graph of my hyperbola. Let me make that last branch a bit better. There you go, this is better. Okay, so this is my hyperbola. I like to put the equations by the side. So it's x squared over 36 minus y squared over 9 equals 1. I like to do that. I don't have to draw the foci to find the equation, but they do ask me for the equation. So if you go back here, right? So they do ask me for the equation or the asymptotes, and they ask me to locate the foci. So I did graph it already, so this part here is done. Now I need to locate the foci and then equation of the asymptotes. So let's do that next. You have a better drawing here. Let's find the equation of the asymptotes. If you recall the equation, which was x squared over 36 minus y squared over 9 equal to 1. You always take whatever is underneath here, right? So this is b squared, so this is what's going to be, right? So the equation is going to be plus or minus b over a, because whatever is underneath y comes first. Okay? So the equations will be 3 over 6 x or y equal to 3 over 6 minus 3 over 6x. So this is y equals 1/2 x. And I say and or it doesn't matter. It's just two things, right, that we're listing, so I guess and is more appropriate. Just these are the equations of the asymptotes, okay? And the next, so there you go. There are the asymptotes right here. This is done. Previous slide. Sorry, a little disorganized with the slides here. But now the next thing that I'm trying to do is find the foci, right? And the foci are given by c, and then c squared is a squared plus b squared. So c squared equals to 36 plus 9. C squared equal to 45. C equals to the square root of 45. I can simplify that as 9 times 5, right? So that's 3 root 5. So the foci will be determined by c. Note that the axis is horizontal, so I'm adding c in the x coordinate. So that will be minus 3 root 5 comma 0 and positive 3 root 5 comma 0. So these are the foci. I don't have to draw the foci if I don't want to, but I can, and they ask me to do it in this problem, so I do have to do it this time around. If they just ask me to graph it, I don't quite need the foci. All I need are the two asymptotes and the vertices. which is basically just A and B. Okay. One more thing I wanted to say is I wanted you to notice how, so 3 root 5, right, this is the same as root 45, which is just over 6 between 7 and 6, and that's where the circle point here is as the foci, right? So just keep that in mind. It's possible for you to locate precisely where, not precisely, but roughly where the foci are. Okay, this is what happens when you have to recenter the equation. All you do is you subtract the coordinates of the center within, the square part. That's the only difference. Everything works out the same. You just have to draw the rectangle center at the center. So rather than just going to A, you just add A from K. So like, see the foci, add C towards K, towards H. If it's horizontal, if it's vertical, you add C towards K. Same for the vertex, right, for each vertex. And this is for the case when it's vertical. I'm not going to talk much about this. I think you're able to sort of understand this. Here's an example of where you can find, or how you can find the center to begin graphing. First thing you got to do is complete the square. So you got to look at this x and this other x that you have here, right? And you got to complete that. So let's see. That's a 4x squared minus a 6x minus a 9. So group the y's. I got to do the same with them, right? Y squared minus. Do I want to do that? Yeah, I do. Gotta bring the negative outside with them. That's a minus 153 equals 0. So what you want to do in here is you want to complete the square. You want to make it so like this is a perfect square, right? So keep that for now. X squared minus 6x. And then half of 6 is 3. So this, you square 3, so that's a 9. So that's what you need here. So 9 times 4. That's a 36. So you gotta add a 36 on the other side. Right? That's how you do this. So that's a 9. So y squared. Half of 10 is 5. 5 squared is 25. Add a 25. Minus 9 times 25. That's a, I know what that is. That's a 251. So 225. So that's a negative 225 because of negative 9. So we've got to add a negative 225 to the other side. Okay? And the reason, so this is the artificial term that I added. Right, this plus 25 is the artificial term that I added. And then as a consequence, right, I needed these two guys. So I'll add 36 here, just so you know where they're coming from. Change the colors. Okay. This guy comes from this, and this guy comes from this. And now I can easily see that this here is x minus 3 squared, which is the whole reason why I did this. Minus 9 times this is y plus 5 squared minus 153 equal to, so what's that? Minus 36 on this is minus 11. That's minus 189. That's what I think it is. Could not be. We'll get it solved. So I can already see, right, that the center is, so the center is already, so I'll put that in different colors so you can see, because I still have to continue my equation, right? But I can already tell that the center is positive 3, negative 5. I can already tell that, right? Based on what I got from my completing the squares. We've completed the squares before. Just make sure that you understand. So if you continue, ultimately you want to have a 1 on the right hand side. So let's see what we can do about that. So that's an x minus 3 squared minus 9 y plus 5 squared. So you're going to add that 153. That's a 6, a 36? Negative 36? Is that what it is? Yeah, I think that's what it is. Okay, that's great because 36 is a perfect square, so maybe things worse. It's also 9 times 4. So when we divide both, so multiply both sides by -1, first of all. You know how that's important for hyperbolas, right? Which sign, each term gets. So it's important that we have a clear view of that. So now I can already see, I can't quite see that clearly yet. I can already see that y is going to be the term that's positive, so it's going to be vertical transverse axis. So we're getting there. Now I divide both sides by all terms, really, by 36. Because I need a 1 on that side. I want to make that a 1. Right, and I do. And then this minus 4, that's a minus x minus 3 squared over 9. And this is a positive y plus 5 squared over 4. Okay, so I've got my equation here. You really want to avoid, so let me write that better. So I really want to avoid to have the first term being the negative, or the one with the negative sign. So I really want to avoid that. So like I said, now that things are the way they are, this negative sign tells me that this is a vertical transverse axis. So this is how my hyperbola is supposed to, I mean, not necessarily like that, but looking like that. So now find A, I find B. So this is A, right? A squared is 4, A equals 2, always the one underneath the positive term is A squared, and then B squared is 9, B equals 3, B is the other, B squared being the other one, C squared being A squared plus B squared, that's 4 plus 9, 13, C equals the square root of 13. Remember, I don't need that to graph it. Now my last step to graph things is to do this. Let's start from the center. So the center I found a while back, it was a positive 3 minus 5. I can also see it here, right? Positive 3 minus 5. Remember, we always have to change the sign of these things because this is supposed to be x minus h, x minus k. So again, positive 3, negative 5. So I go 1, 2, 3. So this is positive 3. 1, 2, 3, 4, 5. It's negative 5. This is the center. This is where everything begins. So looking at this, I can see that this has, like I said before, a vertical transverse axis because y is the one with the positive sign. So I move A, right, 2 and 2 in the y direction to get the vertices. So from here I move 2, sorry, in the y direction, right? So this way. Okay, this is minus 3, and then 2 underneath. This is minus 7. Okay, and then I move B left and right. So I'll go back to black because that's not going to be B, it's not going to be part of my graph. But then B, what was B again? B was 3, right? So I move B this way, and then 1, 2, 3, right? Because B is 3 this way. So this is 6. So I draw my rectangle. It's already drawn, and then my asymptotes are these. I don't need the equations of the asymptotes. You can get them. You don't need the equations of the asymptotes. All you need is the points that they go through, and now you're good. Because now you know these are the vertices, and you know they're supposed to approach the asymptotes like this. Like that. You're good. You got a pretty good graph there. Okay, so it's the same process more or less. You just start from the center to do everything. So they give you the points. You have too much space here, so I'll just cross the extra pages. Better be safe than sorry, right? So there's what you have. Some intermediate steps. They give you the equations of the asymptotes. So the difference here is that you gotta add, the two h and k values. I'll let you fill these out as you find need to, though it's not very important. And there we have it, the 13, everything else. You don't quite need all that unless they ask you to. Like I said, all you need is to draw everything correctly. So let's do this applied problem here. It's the last thing that I'll do in this video. So here's the idea, okay? And let's throw back to what I said at the beginning as the last objective, which is part of solving problems, which is recognizing parabolas from verbal descriptions. So let's read this, and I'll say where the trigger for using, I said parabolas, for using hyperbolas is. So let's read this. An explosion was recorded by two microphones that are 2 miles apart. So we have somehow two microphones that are 2 miles apart from each other. Microphone 1 receives the sound 3 seconds before microphone 2. That's what triggers hyperbola. Microphone 1 receives the sound 3 seconds before microphone 2. You know the speed of sound, they're going to tell you. That means, however the distance the sound goes in 3 seconds. So let's find that distance. So sound travels 11,000 feet per second. So in 3 seconds, sound travels 3 times 1100, which is 3,300 feet. So this is how much farther from microphone 1 the explosion was than from microphone 2, right? So let me say this again. Because microphone 1 received, I said it backwards, let me say it again. Because microphone 1 received the sounds 3 seconds before microphone 2, that means the explosion was closer to microphone 1 than to microphone 2. And how much closer is given by the distance, by that distance, which is 3,300 feet. So the distance from the explosion to microphone 1 is 3,300 feet smaller, right, than the distance from the explosion to microphone 2. So this should bring you back to the initial definition of hyperbola, where I say the difference of the two distances is constant. Okay, so this is what triggers hyperbola, and I'll say that, and you should listen to this explanation and ask about it as many times as you need to make sure that you understand, because this is really what allows you to solve applied problems using hyperbolas. Okay, so cool. So we have the possible distance, determine the possible locations of the explosion. This is really asking for equation of the hyperbola. Okay? So let's begin. So let's begin by putting the microphone in a coordinate system. There's no problem drawing. It's not perfectly vertical. Doesn't have to be. Just want to be a bit better. So we have microphone 1. I'll place it here. I have microphone 2. I'll place it here. I'm also told that two microphones are 2 miles apart. So that means this has got to be minus 1 comma 0. This has got to be positive 1 comma 0. Okay? Good? So remember, in the description that I gave you before, the points where you measure these distances from, right? The distances which, if you subtract to get a constant, these are the foci. So these two are the foci. Okay? So go back to the beginning of the slideshow if you need, which means C equals 1. So that was already a lot for me. That's great. Okay? So that also tells me that my hyperbolas look like this, right? Because the foci are always across the transverse axis, so the transverse axis has got to be horizontal. So we'll write that. So it's horizontal transverse axis. So they're like this. And now I have to find the foci. Okay? Sorry, to find the vertices. If I find the vertices, I find A. If I find A, I can use C squared equals A squared plus B squared to find B. And then I found the equation. So how do I find A? Okay, so this is going to be minus A comma 0. It's going to be positive A comma 0, this other point right there. So let me place it a better place. So this here is going to be positive A comma 0, this guy right here. Okay, so this is one possible location. Anything on that hyperbola is a possible location for the explosion. Okay, so this is why finding all possible locations is the same as finding the equation of the hyperbola. Okay, so let's pick this first one. So A comma 0 is a possible location Is it really? Let me pick the other one, actually, and let me explain why. If I go back to the problem, they say microphone 1 receives the sound. Microphone 1 receives the sound 3 seconds before microphone 2. So my explosion is closer to microphone 1 than to microphone 2. So this part here doesn't really work. Only that branch of the hyperbola works. Okay? So I'll do this. I'll just dash it here so you know that it really is a hyperbola, but this should not be part of my graph. So this is the point that I'll be using, okay? So negative A comma 0 is a possible location for the explosion. Okay? What's the most important thing? The next important thing is the 3 seconds. So the 3 seconds, which gives me the 3,300 feet. So that means this distance has to be 3,300 feet smaller than this distance. Okay? So distance to M1 is 3,300 feet smaller than distance to M2. So, right, this distance here is the distance to M1, right? It's minus A minus 1, right? So just subtract these 2 points. This is the distance to M2. So that should be the distance to M1, sorry, the distance to M2, right? So now 1 minus A minus 3,300 feet. Okay? Think about it for a second. This is the distance to M1 here. This is the distance to M2 here. And then the 3,300 is there. Just think about it. Read this again if you need. Make sure you understand what I'm trying to say. I'm just picking one point because this one point is one possible location, and it should help me solve the problem. Find A. And that's all I need for now. So that's minus A plus 1 equals to 1 plus A minus 3,300. So I can move A over, so that's minus 2A subtract the ones, these cancel out. So this is minus 3300, divide by -2 on both sides to get a positive. Is that 1650? Yeah, I think so. So that's A, and now I can find B. Double check to see if that's correct. So let's look a little weird. Oh, I see what's going on there. So let me correct that, because I have this. Sorry about that. Let me correct it. Because I have 3,300 in feet, so this shouldn't be 1, right? This should be in feet. Sorry about that. This shouldn't be 1. So it's in purple. This should be really converting 1 mile to feet is 5.2. Just double checking because I don't want to mess it up. So that's 5,280, right? Just double checking to see if I didn't make a mistake. Yeah, 5,280. So that's, if I zoom in a little bit, it's minus 5,280, 0, and this here is positive 5,280, 0. Yeah, sorry about that. Instead of that 1 over there, you should really have, a 5,280, which doesn't make a difference for us because they cancel out anyway. I just want to make sure that I write things correctly. So that's minus A minus 5,280, and then 5,280 minus A. Just want to put the 5,280 there. I'm doubtful that they really cancel out. Yeah, they don't really cancel out. Yeah, so these numbers do matter. Let me just read it again so that I don't mess it up, okay? So that shouldn't be a 1 and a minus 1. That's my mistake. So it's minus A minus 280. Yeah, and no, they do cancel out because it's minus. So they do cancel out. So it's minus A. This cancels out with this. Equals 2 plus A minus 3,300. Yeah, that's right. Okay. Still holds. Sorry about that. I just messed up forgot to convert to feet from miles. That's my bad. But anyway, now I find A, and I have C, which is 5,280. Because it's not in miles, it's in feet, and now I can find B based on that. Right, so B, to finish it up, B equal to, so I use that A squared equals, A squared plus B squared equals C squared. So I have 5,280 squared equal to 1650 squared plus B squared. I'm going to need a calculator for that for sure. So B is going to be the square root of 5,280 minus 1650, each of those squared. So plug that into my calculator. So that's the square root of 5,280, that squared, minus 1650, that squared. And then I get approximately a 5016, I'll say, to the nearest foot. So that's B. So that gives me B. Okay. So all I want really is the equation of the hyperbola. So the equation is, remember, I have it on horizontal, don't quite need it. So I have x squared over a squared, which is 1650 squared, minus y squared over b squared, which is what I just found, which is 5016 squared equal to 1. And then remember that I told you only the left branch of the hyperbola worked, because it's got to be closer to microphone 1 than to microphone 2. Then you gotta say something like x is less than or equal to 0, just to make sure that you have the right branch. Okay? You write that. Let me say one more thing before I close this, because now that I have an equation and I have a set of possible locations, I have a very clearly defined set of locations for my explosion. Still not good. I'm still not doing so good. One thing that I can do is use the other things. Let's say this is happening in real life. You have a microphone 1 here and a microphone 2. How do you actually find that explosion, right? How do you actually find where it happened? We can use some visual cues. You can look at, say, this point, and you can try and find. So let's say I can see the explosion happening here. How do I actually find its coordinates, its distances, and everything? I can look at angles. So I can start by looking at this angle here, and then I've found precisely. So if I can measure this angle, now I know precisely where the explosion is, because there's only one point where that line meets the hyperbola. Okay, so there's another use for trigonometry, another use for hyperbolas and everything. I'm closing this right now. This is extending a little bit longer than I intended. Sorry about the little error here. Please make sure that you correct that in your notes. Next time we're going to study another conic section. Thank you for watching this, and I'll see you next time.